My name is Tommy, and I'll be talking about yield stress. We've discussed that one identifying feature of a fluid is that it doesn't have its own shape and instead takes on the shape of the container. An interesting consideration is then the example of mayonnaise. If you pour it into a container, we can see that the bottom part of the mayonnaise conforms to the shape of the container. On the other hand, the top part of it does not. This is due to the yield stress of the substance. Yield stress is a shear stress below which the substance displays rigid body behavior, and above which the substance displays behavior of fluids, in which there is continuous deformation under shear stress. One way of quantifying this is by measuring and plotting the shear stress against the shear rate of a fluid. The yield stress is the shear stress experienced before there is a significant shear rate, or in other words, the y-intercept of the curve. We can see that the red curve of the Newtonian liquid has yield stress of about 0, as we would expect with something like water. The blue curve happens to be a class of substances that have significant yield stress, called Bingham plastic liquids. These are named after Eugene Bingham, who proposed its mathematical form in an experimental study of paints. The significant yield stress in Bingham plastic fluids occur because there exists an internal structure of the substance that creates a weak solid structure, which then collapses above the yield stress to exhibit liquid behavior. Examples of other substances with significant yield stress include paint, which allows for unique brushstroke patterns when painting, and toothpaste, which requires you to squeeze the tube before flowing out of the opening. A solid understanding of the factors affecting yield stress allow engineers to optimize substances for applications. For example, if the yield stress of paint is too high or too low, it may negatively affect the artist's creative process. A solid understanding of the yield stress of substances also allows engineers to properly model their behavior. This aids engineers in manufacturing processes of different gel-like substances. Another interesting application is found in cement pouring, where an understanding of yield stress allows engineers to predict whether or not bubbles will rise out of the cement mixture, a factor that greatly influences structural integrity after it sets.